all right, okay. Thank you for the introduction. Maybe let me quickly introduce ColdStream and what ColdStream exactly is. ColdStream is basically a tool or design tool that can be used for thermal engineers throughout the entire design process. So this means that a thermal engineer can use ColdStream in the very beginning of their process, but also in the very end when they want to have very detailed designs and so on that need to be manufactured completely. The purpose of this workshop is to give you like an overview of all the capabilities of ColdStream and how you can actually use ColdStream as a support during the design process of all your thermal components. Okay, so let me dive in. What you see here is already the home screen or the landing page. When you enter ColdStream, when you're logged in, this is basically the first page that you see. Basically, just here you see a few projects that were created. This is a demo company. But let me already dive into a project. This is a double stacked battery pack. So this is basically a battery pack that needed to be designed to cool batteries for an electric vehicle. And the problem was the engineers want to create a design for this cold plate. So basically fluid flows in and the system needs to be cooled. What you already see here are two cases, we call it. Each case represents a calculation that has been performed on high performance computers. So like it's not calculated on your own computer, but this is really like an online web platform. And in the background, all your calculations are performed on high performance computing modules. So in order to ensure that you have the correct amount of capacity for your case, because each case also represents a lot of CFD simulations in the background, which of course needs some resources for your calculation. All right, okay. I will show you first of all how to do an easy simulation. I already prepared some that are finished just to like be a little bit more fluent. But the first thing we do is you go in the case, or maybe I can show you what you do like when you need to create a case first. So the first thing you want to do when you start a case is you click the Add Case button. Here you give it a name. And then you can basically select the case type. So here you basically see 3 different case types. And first of all, you can do a simulation. This is just a CFD simulation, which is usually used to assess the performance of a design that you already have. Then you have a standard design option. So with this standard design option, you basically start from an empty design domain and you optimize your cooling component, but for a standard design. So this means that the designs that come out of it or pins can be pins or fins. And the third option is a custom design. And for a custom design, the optimizer has the complete freedom and it can return shapes that are like besides pins or fins, but it takes into account your manufacturing requirements. For example, if you want to 3D print it, if it needs to be a sheet metal cold plated stamped, if it's die casted, and so on. But I will show you examples of all those 3 options so that it will be more clear for you. Once you have selected your type, you click on Add Case. And then basically the next thing you need to do is you upload your geometry So basically, the preparations that you need to do in your CAD software is to prepare your geometry with regions and boundaries, but I think it's best if I already show it for a case that is set up, so it will be more clear for you. So you see already the regions tree, and this is basically what is built when you upload your CAD geometry. So usually your CAD geometry exists of a few components, like the housing. In this case, we have a battery pack housing, and then we have battery pack modules, and we also have a fluid region. And then you also have some surfaces to indicate the boundary conditions, for example, an inlet and an outlet. So here you see the geometry. In this case, we have a battery pack housing. We have a fluid region. So here we just want to assess the performance of this existing design. That's why we started the simulation. We have the outlet, which is, it's not really visible. It's on this side, and an inlet on this side. And then we have one battery pack here and the other one here. So it's basically a cold plate in between two battery packs. Then additionally, you also see some interfaces. These are also automatically detected just to indicate the interfaces between different regions. For example, the interface between a battery pack and a battery pack housing. And that's basically the first step that you do when doing case setup, is basically uploading your geometry. Now we've done that. So then the next step is to define all the boundary conditions and also to assign some materials to your case. And what we actually wanted to do is to keep the case setup as easy as possible. So that's all, like, so that you don't need to be an expert to really know what kind of settings you need to do. It's really the purpose that a case setup would only cost like 10 minutes for you to do an entire setup, and then you can just click on a button and you can submit your case. So in this case, for the fluid region, we have assigned a water glycol mixture to it. And that's basically the only setting that you need to do here. Then for the inlet, we just selected a boundary type, which is a pressure outlet. And for the inlet, we set a pump inlet. We needed to define the inlet temperature. And then you can also select a pump. In this case, we selected a Bosch electric cooling pump. But if you have your own pumps, you can always define in the libraries your own pump. You can upload your pump characteristics and so on. Then for the battery pack itself, we assigned a material lithium corrected. Yeah, this is the name of the material. And we also apply a volumetric heat source to it, which is 5,000 watts. And the same for the second battery pack. Also, the material settings, you can just define your own in the libraries. And then for the housing itself, we just applied the material to it, which is an aluminum alloy. And that's basically it. Those are the settings that we need to do. Suppose that you have like a thermal interface between the battery pack and the housing. You can also define it then in the interfaces. You can select an interface. You can select an interface that is also in the libraries, or you can define your own interface. And then basically we're ready to submit. When you're completed your setup, you will see green check marks, and this means that all required input is completed. and then you will be able to click on the submit button. Now, in this case, the case was already submitted, so I cannot click it again because it was already finished. But maybe some important thing to tell you is that when you click on submit, you have a few options. Maybe I can show it quickly. Let's see if I have a case setup that's not. Probably I had to take the other one. This is for, but I can show it here. So when you click on submit, then the first thing what happens is the case setup is being validated just to see if all your settings make sense. And then you have a few options. Now in this case, it's a standard design, but for simulations, it's quite similar. We have an option to do a correlation-based estimation. This is basically an analysis, a thermal analysis based on a thermal network. So a thermal network is generated, and based on this thermal network and some correlations, the temperatures of your case are estimated. So this will give you a first rough estimation of the performance of your design. When you do this, it only requires a few minutes for simulation to get the results of your estimation. And then you also have a conceptual or a detailed CFD-based option. And that's basically means it will do like one complete CFD simulation, but the difference between conceptual or detailed is basically the resolution level of your case. Conceptual is a lower resolution and the detailed is a higher resolution. And you can also control the speed, like the resources that you assign to your case just by dragging the slicer, and you assign more credits, then the speed will increase. All right, okay, so that's basically it for a case setup of a simulation. Once your case setup is done, and once your case is finished, then you basically can easily look at your results also via the platform. Let me show it here. So you already saw a sneak peek. Here you have just a case summary page. Yeah, you can have a quick overview of some temperature graphs and so on. Sometimes it can happen that your case is running, but you get a warning because, for example, one of your settings is practically infeasible or something, and it can be that you see like a warning message over here. And then the next thing that you can visualize is the thermal network itself. So the thermal network basically visualizes the thermal network of your case. You can see like the thermal resistances between regions and so on. And basically with this thermal network, you can also evaluate the how should I say, the impact of certain parameters. Suppose you want to change your inlet temperature or the power of your battery pack module. You can do like quick estimations and see how this would affect the results of your case. Additionally, you also have some table views where you can just see the values in the tables, temperature, pressures, and so on. Some 3D results. I'm just quickly going through this because I also want to show you some other stuff. But here you can visualize your results on your geometry. Basically, might take over My screen is sharing, can take a few moments. Maybe I'll show it for the next cases for one of the designs, because I think this battery pack is like the most heavy one to load. So, but that's basically it for doing a CFD simulation. It's very easy to do. You already have your complete simulation setup, and when you submit your case, you can already have your estimation results within a few minutes. For like conceptual or detailed simulations, it can take up to a few hours to a few days. It depends on your case setup. Suppose you want to include some radiation effect or some buoyancy effects, then the calculation time can increase. But it will always show you on the slider itself. All right, okay, so that's what you can see for a simulation, or what you can do with your simulation. Let me now go back to the project and show you what to do if you want to design. Oh, yeah, I think my computer is a bit slow. I hope everyone can still hear me.
Yeah, works for me.
All right, okay. Yeah, it's usually when I'm sharing my screen that my computer does not have. Ah, voila. Let me just go back here. All right, okay. So that was it for simulation. Suppose now you have like a Raspberry Pi, because that's the next project that I want to show you. Suppose you have a Raspberry Pi and you want to like design a heatsink for your Raspberry Pi, but you don't want to have like you actually basically want to have a heatsink that is just available off the shelf. You don't want to have like any fancy design or so on. Just pins and fins, it's good enough for you. Then the next thing you should go for, or you can start with, is to do a standard design simulation. So yeah, here you see basically a bunch of standard designs have already been created. But let me show you one of those. Let me show this one. And now I will just go back again to the case setup. Now we don't have a design yet, but we want to have ColdStream get the design for us. So what we do now is we don't upload a design in our geometry, but we include a block which represents the design region. And the design region is basically the region which indicates where structures can be formed. So here again, we see our case setup geometry. We have a cover, a CPU, which need to be cooled, some RAM, yeah, some external connections, a housing. We have one heat source over here, another heat source over there. Then basically this region is the coolant. So it's basically, yeah, in this case, air will flow here. So this indicates where air flows. And then here you see some blocks which are called design regions, and basically these blocks indicate the space where a heatsink can be placed. We have one design region here, one here, and one here. And then basically we have a lot of additional boundaries, which actually are the outlets in the air where the air can flow out. So yeah, those are all the boundaries. And we have an inlet over here. Then for the case setup, basically the case setup starts completely the same as a case setup for a simulation. But what's very important now is that we also need to define or design targets, because of course you want to design for some requirements, and that you can do also easily in the case setup by just indicating your target. Here you already see the icon, which is indicating where some targets were set. Now in this case, we want to minimize the temperature of the CPU. So we have assigned a temperature minimization target. We also want to minimize the heat source of this, the temperature of this small heat source and the temperature of this heat source. Then additionally, you can also impose some constraints. But in this case, no constraints were imposed. But in some cases, you can, for example, apply a pressure drop constraint. If you have a fan inlet, it doesn't really make sense to apply a pressure drop constraint, but sometimes you can have like a fixed flow rate inlet, then usually you can apply a pressure drop constraint. Other targets or objectives that you can add are, for example, temperature variance minimization or temperature variance constraint. That's for especially for battery cold plates. This is used a lot because there it's very important to have like a variance which is very limited to increase the life cycle of the batteries. You also can do a volume minimization. That basically minimizes the volume of the structures that are added, just in case you want to like minimize the mass. And then you can set a temperature constraint on certain boundaries. But just in this case, we applied 3 temperature minimization targets. Then again, like the simulation, once your case setup is completed, you submit your case, and then you will see how long it takes until it's finished. And when it's finished, you can go back to your case and you can look at the results. So in this case, let me show you the design evolution tab. This is basically for standard designs available. And in this page, you can see the evolution of the design process. So while the case is running, you will be able to already follow up the different iterations of the optimization process. So what you see here is each dot basically represents an iteration. The colors also represent if the result of this iteration is feasible, and the green ones are the best feasible iterations so far. So if you have a red dot, then it means that for that iteration, some constraints might be violated. Now, in this case, you see this one is the last green dot, so this means that this should be the best feasible design. Here on the bottom, you can also already see the designs that come out of it. You have some info of the design parameters that were used. Also, you can also assign multiple material options, and then it also selects the best material for your design. And in this case, we selected pins and fins. You can also select if you want either only pins or if you only want fin designs, or if you want one of those two, then it just selects the best one for your application. And then here on the top, on the bottom, you can see a few graphs which basically represents all the targets that you have set. So in this case, we set 3 temperature minimization targets. And here you see the graphs representing the target values for each target that was set. Suppose you have a constraint, you can also see the constraint that was imposed and which points are feasible and which are infeasible. But in this way, you have like a very easy and interactive way of selecting the best design that fits your requirements the best. If you want to download the step files, you just click on download design, and then it will download the step file of this iteration. You also see a download results button. With this, you will actually download the complete simulation files, which you then can visualize with your own post-processing tool, like ParaView, for example, can be used to then visualize your results as well. All right, let me quickly see if the 3D results, if it's faster to load them over here. Yeah, for this one, it's easier. Let me show you the designs. So here you can also actually visualize the streamlines. Let me give them color. So here you can basically select what you want to visualize. In this case, we want to visualize the velocity on the streamlines. So here you already have like a nice view of the streamlines. I can show the design regions as well. Yeah, I have the idea that it's a little bit lagging, maybe because of the internet connection. But I can quickly show you this, for example, the housing. You can basically really visualize the temperatures and so on. You can also visualize slices. And in this way, you can basically also see like which iteration will be the best one fitted for your needs. It's usually it will be probably the best feasible one. So the last green dot is basically the best one, but it might be, for example, if you have a constraint that is like a little bit violated, but it's yeah still okay for you that you like take another iteration than the one that was proposed. All right, okay. So that's basically it for the standard design. Now, the next thing that I want to show you is the custom design. So you can think of like, okay, I can create standard designs, but I don't, standard design is not really fitted for my needs because yeah, your cooling is way more critical. A standard solution is not sufficient for you. For example, if you have like a battery pack that needs to be cooled, then yeah, with pin or fin heat sinks, that will not fit into your application. And cooling is really critical. You really want to push your design to the limits, then you can go for the custom design option. And the custom design option is basically, it basically starts similar as a standard design, but let me show you the case setup. But instead of like now, yeah, this one is already finished. But instead now, like selecting pin or fin heat sinks, you can select the manufacturing type. Let me show you probably this one. Ah, this was the standard design, sorry. So for custom design, you basically prepare your geometry the same way as you do for a standard design. So you just define your design region again, your coolant, housing, and so on. But here in the design region itself, you just specify your manufacturing type. CNC, mills, 3D printing, die casting, sheet metal, or an electric wire. Electric wire is usually used if you want to like heat something. And then you also just select some manufacturing settings. Again, you can define your own in the libraries if you want. But then for the rest, the case setup is similar as a standard design. Here, for this inlet, we have set a pressure loss constraint. And we have a temperature minimization target for this heat source and another temperature minimization target for this heat source. So basically what this application is, it's a coolant, a heat sink to cool down some like power electronics on both sides. And fluid flows in from one side and it comes out from the other side. And now we just want to design the internal channel structure in between. All right, okay. So once your setup is completed, back again, press the submit button, your case setup is validated. And then once that's done, you again have similar options. In this case, you will not be able to do a correlation-based estimation. You will only be able to do CFD-based design runs, but you can select a draft, conceptual, or detailed design. A draft, the draft mode is basically to validate the physical case setup. So, for example, you have a case and you don't exactly know if these targets will fit well for this application. You can do a draft design, which is faster than conceptual and detailed, but already gives you like insights in how your case setup is valid. And a detailed design is like on very high resolution. The design will be completely manufacturable. You will be able to download the step file, which contains the complete channel structure and so on. All right, so once you've submitted your case, then again, you wait a few days, and when it's finished, you can take a look again. Now in this case, we started it 2 times, one for 3D printing and CNC milling. This is basically also to just show you how flexible ColdStream is and how different your designs will appear when you like select a different manufacturing method. Let me first show you the CNC milled design and how it looks like. So again, here you see the regions tree. And here again, with your step file, download results, you can visualize them with your own post-processing tool. Okay, for one moment I thought it would not work. All right, maybe it's best to immediately show you the design itself. So this basically, here you can already see it. This was basically run as a conceptual design. So it's something in between a draft and a detailed. It might be that it's not 100% manufacturable yet, but the results are accurate. You already have a very good impression of how your design looks like and so on. Maybe I'll also quickly visualize the streamlines. So you can visualize the pressure drop of your design. You can also visualize the velocity and so on. So here, basically, you can see that the flow comes in through here. And then you see basically that the channel structure that has been created like this to minimize the temperatures on both sides of the geometry. And this design is like CNC millable, so it's designed for CNC milling. And of course, yeah, a tool size was also applied in order to take into account the tool size that's required for milling the channels. But then basically that's it. You just have your design, you download it, and you can have it manufactured. Now I will show you the difference with a 3D printed design. So this one is a 3D printed one. Let me load the results. Okay, so again, looks the same, but now let me show you the 3D printed design. I will visualize temperatures again. So here, basically, you see that the design is completely three-dimensional. It looks maybe a little bit similar, like the CNC milled one on top. You can imagine that it's like the same case, but here we have like a completely three-dimensional channel structure, which can now again just you download design, you download the step file, and it can be 3D printed because it also took into account all your 3D printing settings. Let me quickly also visualize the streamlines over here, just to show you. Like this. So voila, you can see inlet, outlet. And this is basically how the three-dimensional design looks like. Okay, good. So yeah, I think these two cases really show you the difference between manufacturing methods and also like the capabilities of the custom design of ColdStream. But for this case, always some heat was involved. The targets were to minimize some temperatures, but ColdStream is not only limited to that. It also can be used for pure flow optimizations, and I also have a few examples for that. Here I have a manifold. So in this case, let me show you the case setup and the I can show you this one. So in this case, we have a manifold with 4 outlets and 1 inlet. And this is like the standard design that was designed by some engineer. But in this case, we actually want to minimize the power dissipation. Well, that's also possible with ColdStream. Also, like there's no heat involved, but that's also possible. I will show you the case setup for that one and how to start this problem. So here again, we defined an air region, but in this case, it's like a block in between the outlet and the inlet because we want to give some design freedom and we want to have the channels or the connections between the inlet and outlets optimized. So this is the air region. The design region is like this solid, this block in between. Then again, we have the outlets defined and we have the inlet defined. And on the design region, we set a relative volume maximization because we wanted to maximize the volume of the material that was added. And in the air region, we set a power dissipation minimization target because here we really want to minimize the power dissipation. Once that's done, and once you have completed the calculations, then again, you can look at the results. Voila, and so basically here we can see what comes out of it. So here we basically get a completely shell design, which is actually like an optimized design compared to the control. So here you see the connection in between the channels. This one was also a 3D manufactured case. So it's completely three-dimensional with like very organic shapes. All right, and now you probably wonder, is this design really better than the original one? Well, we can also compare those. Yeah, here you can see I already put them in comparison, but let's compare them. So in this case, we wanted to minimize the power dissipation. So this is the optimized case. Here you can see that in the inlet, we have a pressure drop of 119 Pascal compared to the control simulation which had a pressure drop of 350 Pascal. So indeed, really the optimized design is better. In this case, we didn't set targets to like have same outflow in all of the outlets. So that's what you see here. But it's also possible to set a constraint on the outlets so that the flow rate on the outlets is similar basically. All right, okay. That's it for the custom designs. I don't know if I should still like leave some room for some questions. If so, yeah, we can do a question round, or I don't know if that's like the purpose or not. Post your questions,
Yeah.
Roxane. Ah, yeah, okay.
No.
All right, okay. Thanks everyone for having me, and yeah, feel free to ask me some questions. I can also show you how you can apply for a student license, because after this, like a small homework will still follow, but you can request a student license for this, and that's basically via our website. Let me show you how you can do that. Wait, this is not the correct place to request the student license. Well, our website is just recently updated, so there was a request student license, but you can also do it via the try now button, and you can request your enter your email address and submit, and then you can get like a demo account.
All right. Great, Roxane. Great presentation. Really enjoyed it. Are there any questions from the participants?
I see one question.
Yeah. Is this session enough for the homework? You know the homework better than me, Roxane? What do you think?
And what do you mean if you will be able to solve the homework like
Probably,
with
yes.
with the explanation of this session?
Yeah, probably.
Yes. Well, I think indeed it will be enough for the homework. And also it's not that like ColdStream is a very complicated tool. It's actually designed to be very user-friendly. You can also, if you have any doubts, you can also always go to our documentation page. There you have like an extensive explanation of all the options and so on. But yes, it should be enough for the homework.
Some no more questions. People are very silent these days. Yeah, all right. I think with that, we can wrap it up if there are no more questions. If you have any other resources, maybe on generative design or some practical applications, case studies, Roxane, that you would like to share with the audience, feel free to do so. I'm happy to put them in the community.
You mean afterwards or now? Or
yeah, afterwards. Yeah, afterwards.
Yeah. Sure, yeah.
All right, cool. Then we'll call it a day, Roxane. Thank you so much again for the presentation. Really enjoyed it, and talk to you soon.
Yeah, thank you very much for having me.